Good. So let's start the video. And we have the recording. And let me share the screen as well. Good. So and I think we are talking about this one. Good. So, okay. So we were talking about the repartition before, and like two important problems that we are talking about. One is repartition. The other problem that is very important is tree sat for proving NP-hardness. And we talk about, some problems, especially the original of this problem that comes from this make a span problem. This generally you will hear make a span a lot when you do the scheduling problem. You want to minimize the maximum processing time of a machine. And that was a very simple reduction from tree partition or partition. As I mentioned, you may start with partitions. Sometimes you can go also prove for tree partition, then you will get a strong NP-hardness. It means that even dynamic programming cannot help, which is important in practice. Now, let's see, some interesting set of problems and how you can use this, guys. So this is the first one, was the rectangle packing that actually we talk about it and mention that, you want to put it like in particular about advertisement. And this is the screen that you have. And you want to put some advertisement boxes there, or this is called advertisement creative. They have a different size and you want to pack it in essence. And this problem, as we discussed, it was, you could show that using this problem, tree partition, that problem actually is hard. Let's see a few other problems. So the other things is like the age matching puzzle. What is age matching puzzle? So you are given a, let me just do these things. So the size of the things is good, correct? You can read it. Good. Okay. So what is the age matching puzzle? So in this problem, you are given some unit square like this, and each side has a color. And then you are given a target rectangle. You want to put the tile in target such that tiles sharing an edge have a matching color. So two colors that you will put it, the other guy that should have the B here, essentially. So this is a puzzle, essentially. So here, as you will see, there is no numbers in some sense. But in some sense, there are numbers. The colors are the numbers that we want to use them. So here, just make sure that, Ali, do you hear me well?
Yes, yes.
Okay, good.
Thank you.
Good. Now, so we want to here use a reduction from tree partition. So this problem we have started with rectangle packing. So we try to use that one and massage it for this pair. So in the rectangle packing, as we discussed, you try to put this all this rectangle in such kind of you want to pack it in this target rectangle. Good. Now we try to use this. Now we have that problem. So we had the tree partition, then we had rectangle packing. This is an important one that is NP-hard or NP-complete. Now we try to use that one. So what is the idea is that for each of these what was the problem that we had it in rectangle packing is that we had some AI that they were like, let me go to the previous page. You can see it better here. See here, we had this problem, A1, A2 to AN, and each of them had essentially like width epsilon. And here, as I mentioned, you can multiply everything by n and get the width 1. You see that case. Please, we don't see it here. Let me just. So this is the case that we had. Good. So note that that's the important thing that I mentioned. Whenever we are proving something in the lower bounds, we always want to prove something is hard, even in special cases. So here, for example, we know that rectangle packing is hard, even for the case that these widths are 1. Good. So that is something that you don't, I mean, that is enough because that is something that you can use it maybe much easier. So here, for example, in the yes. So here we can assume that these AIs, each of them have some lengths and the width is 1. Why? Because we knew that even in that case, the problem is hard. So now how can we make, so we want to form a gadget. We want to, look, we have only these squares here, correct? But, so we have these smaller squares. How can we, but here we have some rectangle of size AI. The question is that how can we create from these guys, these AI guys? So the idea is that actually let's put some gadget and have some unique color. So this is the way that we are doing it. So these are some percentile things that we are putting on top of this. So these percentile are general things that can be matched with anything. These are the color that can be matched with anything. There are some $sign also that we don't want that these guys rotate because they can only come like, they can be just matched with $sign. So like, so if you consider like vertically, they can, this percentile things is working, is the color. And if you want to go horizontally, the $sign. Now, the main important thing is this color I. So we have a color I, which is just unique to this AI. Good. This makes sure that, I mean, there is no other color, there is no other square of color I. The only way that these guys, they can do it, they can match together. And here, it should be the case that because this guy is $sign, is this sign, is $sign, and these are this one, this should be the beginning, and this should be the end. Like this guy should be the beginning, and this guy should be the end. Good. So that's essentially the whole idea, that we are just putting these unique colors. So this guy should be all come after that. So this is essentially this guy. So this should be the case that this should be I, and this should be I. Is it clear? Good. So because this color I should go together, in some sense, if they want to form anything, they should form this rectangle. And as I mentioned, you could assume with a lot of generality that the width is 1. Because we knew that even in this case, the problem is hard. Ali, does it make sense for you as well?
Yes, yes. Thank you.
Yeah, good. Okay, so now the only thing is the target triangle, target rectangle. We need to make sure that that works as well. Good. Now, that's actually, I mean, not hard. So here we will put the $sign here because we know that these guys, they should go horizontally. So we will put the $sign here. We had the length of the width of this is n/3. n/3 is because of the 3 partition. Correct? We knew that, again, we knew that rectangle packing, even for the case that n over is this size is n over 3 and the width is 1, even in this case, it is NP-hard or NP-complete. By the way, I'm talking about NP-hard and NP-complete somehow in equivalent sense here, but because really NP-hard is the main part that makes a problem NP-complete. But anyhow, so that's the thing. So we are putting this dollar sign here, and we will put this percentile things here. And you can also put some kind of unique color here. I don't know, maybe some white color here that you are putting to make sure that they always should form this rectangle at the boundary. Good. So that's it essentially. So what is the, in some sense, by this color, we force that this structure happens. And these are, I mean, these are in some sense, these are the gadgets it is called. So for example, this AI, it is some gadgets that we are creating it for the rectangle. Or this is the gadgets that we are doing for the target target rectangle. So, so in some sense, the frame forces this happens. And what is the target shape side? That would be n over 3, because that's the thing that we have it, times t plus 2. Why t? What was t? T was essentially the size of each bin in this 3 partition. We had n over 3 bins. You can consider it, and you want to put these guys there. And t was the size of these guys. So what's the average size for 6? And what else? And t plus 2. Why plus 2? Because, I mean, we are having 1 here. Sorry, yes. So because we have 1 here and 1 here. So it is t plus 2. The same thing, we have it also n over 3 plus 2 because there is 1 extra here and 1 extra. Good? Clear? So that's the type of gadgets that we are using a lot, and we try to create it. And this, for the games, especially, we are mentioning a few games. These are the type of things that we are doing. But that is interesting, of course. We went from, first we had like the partition, then 3 partition. We didn't mention how you can prove the 3 partition is hard, but that you can read it. But after that, we went through the rectangle packing problem. And then after that, we mentioned from this puzzle essentially. Good. So this is the rectangle packing. The other problem, so this was, the first puzzle name was age matching puzzle. The other one is signed age matching puzzle. What is the same signed age matching puzzle? So it's very similar to the previous case. So these are colors come in a matching pairs. So here before, like when 2 colors, 2 sides have the same color, you could match. Here, they are coming in a pair essentially. So capital A and non-capital A, they can match, but only these 2 guys can match. And non-capital B and B can match, and so on. And a color does not match itself, only it matches its mate. Good. So now the question is, how can we do that? So this is essentially the ideas that you can do it. You can consider this guy as some rectangle which is given to us. Sorry, this is some. Now here we are giving reduction from onsite age matching, like the previous problem that we discussed. Always when we say reduction from this problem, it means that we need to solve that problem using our setting. So in that problem, what was the thing? We had this square with these colors on the boundary. Of course, here we don't have that one. We need to create it. How can we create it? We can actually, for this one, we are putting 4 guys like this. So how do we do that? We are just adding a few more colors for this guy. So we are adding essentially D here. And so this is a capital D here. Then this is a non-capital D here. We are putting Y. These are something that we are putting such as this guy. So this Y can be just special to this particular triangle. So this inside guy that we are putting Y or W's or X's or Z's, these are all special to this square. The rest are the previous colors that we had it. Now, when we put this one, I mean, the inside guys essentially just disappears because these are just some kind of private things that have happened. But what do we have like now in the outside? We have like this one. We have D, capital D, non-capital D. Non-capital A, capital A, and so on and so forth. So now you will see actually we have both colors here. So in some sense, now these problems so we want to make sure that this problem we can solve it essentially. So we want to give a reduction from onsite age matching. It means that we should be able to solve onsite age matching. Now, instead of B, we have just this BB, this color BB. And so instead of like A, we have this color. And now this is the, in some sense, whenever we have B here, because from this one, we created this one. And now it is somehow unique, the same condition. So this was the, in the onsite matching, unsigned one, we had this condition that B should be matched with B. Here, instead of B matching with B, we have the non-capital B, capital B should match with this pair. So this problem actually now can solve the onsite age matching. So it means that it is hard. As I mentioned, these are the unique colors. We need to assemble 2 by 2, assemble 2 by 2 guys. And it acts like a onsite tile. Let's see another problem. This is the one actually I have seen that my children are playing a lot. I am not that fan of them, but you know, this is the jigsaw puzzles. This is generally we have a map, we have a map, we have a face, we have a picture. Then you are just cutting it into squares, and then you need to put it back essentially to make it. And you know, it can be arbitrarily complicated. That actually is one example that this NP-hardness actually is important, because you want to see how much the problem becomes harder when the size goes doubles. So, and this is the whole idea about NP-hard problem, because we believe that there are, I mean, so far the best thing is exponential. It means that if you make it essentially like a double, difficulty, the size of this double, the difficulty goes exponentially harder, not just additively harder. So when you have it, like when you see a big picture that somebody has done it, you appreciate the time that that person has spent for it, or I don't know, maybe waste for it. Yeah, so that's the interesting thing. And this is the case actually the size can become big, and the size, this parameter n that we are talking about. Here, I mean, we are assuming there is no guiding picture. That's actually very important. always that is my children are playing, I said, actually see the guide, because that can help you where you should put them. Because otherwise you are just solving a problem which is hard. So, I mean, we are assuming, I mean, there is some ambiguous. The ambiguous can or cannot happen, but I think we don't need actually in this case to have that one. Even with that, we can say it is hard. Good. Now, let's solve the problem from the signed age matching problem. So we are creating these things from, as I mentioned, from tripartition to rectangle packing, then to unsigned age matching puzzle, then signed age matching puzzle, and now we are talking about the jigsaw puzzle. Good. Now, how can we do this one? So, and that is important. Now, the signed version actually plays a role here. So you have a signed age matching square like this, correct? How can we turn this this one to this case? That so here that's the idea. So the lower case becomes essentially pocket like this one. It goes the inside, and then the upper case becomes a tab like this case. So here, so this, and I mean, say that you can still have the colors as well. So I mean, we will talk even the version that you don't have the color, but here say that you have the color. So color A should matches color A. So here, then we don't need essentially to have this color capital A here, because we can just make it, I mean, the color non-capital A, because it is already a tab. Good. And only, I mean, you see this area, the color should match with the area of the area of the, so if this is, if let me put it here. So if we have these things here, so these two colors should match in some sense, and they both can have color A. So essentially, when we have this capital, non-capital, we turn them into pocket and tabs. And good. Now, what can you do even more than that if you don't want to even have the colors? You don't need to have the color. For each different color, you can have a different pocket and tab that they only match together. For example, I mean, you can consider it like at the different places. So it might be at the different places. Like this guy, for example, if you have this. So this is for A, color A. This is the for color B would be here. Or even the shape of them can be different. So for example, this one, it can be like this, while the other one is just straight. Good. So the shape, yeah.
But then if these shapes are like unique to a particular type of pocket,
yes.
Onto a particular type of color, then isn't this problem key, because for each pocket you look for like the unique
no, but I mean the color A still can appear in lots of these guys. So this color A, it may appear in several of these squares.
Oh.
So to which square you want to match it with, each square still is the hard problem. Good. So here, so as I mentioned, there are two ways. You can have it might, because they are matching, generally they are pictures or something, so they have a color. So if you want, you can use the color version, that these have the same color, as I mentioned here, these are have the same color. Or if you don't, even if you don't have any colors, you can have this one that they have just a different shape at the different places, that they only can match their things. Just the angle can be different, essentially. And actually, this is one of the things that I don't know. How many of you have played this Jigsaw puzzles? How many of you have done it last year? Yeah, so that is actually interesting because, you know, I mean, like especially my daughter is very good at doing these things. Sometimes I try to help, but this guy, you try to put them and they are not going to each other. You try to force them and say, maybe they should go together. But because of these different angles that they have it, they are not, like very similar, like almost the same, but not completely the same. You really need to find exactly the same. I think they are doing with the cutting this machine, so they know exactly which angle you need to do it. So it seems very similar. They should go there, but not completely match. So you need to actually find the actual match for that one. And I said, oh, Daddy, you should not put these two together. They are not really the matching pairs. But anyhow, so that's actually interesting. Now, one other thing, also for the boundaries, we had such kind of like, for the boundaries, for example, if you remember in the previous problem, for this boundaries, like in the text, this is for the, this is for the targets rectangle. There we have this one. For this guy, you can actually have it some shape like this. This make sure that, I mean, so if some guy is in, so this is like this part is in the boundary, then you will put it this one. So no tab, no pocket. This make sure that these guys only go to the boundary, no other place. And that actually exists. So from this, you can see if there is no tab or no pocket, they should go to the boundary. So this is yeah, so this is actually the result Jigsaw puzzle. This was a paper that Eric Demain and his father. So that's, we have the book together, and also, I mean, he was my ex-advisor at MIT, and this is his father actually that they have written paper together. This is, I mean, a nice problem, and there's a community actually. There's a conference called FUN, F-U-N, that they are publishing, I mean, more of this kind of game. I don't call it game theory, these are game stuff. That for these games, you show that these problems are hard. And these are not trivial. And I was talking with Eric recently and say, some of them actually people proved it. And now Eric mentioned that he was trying to essentially teaching in the class, and then I said, oh, there's a bug here. And then the gadget may not quite work. So these are not easy things because you need to check lots of conditions. And this is like a proof essentially, but the proof of lots of boundary cases that you need to do that, and it can be complicated. Any questions? Okay, so let's go to the next problem. So the next one that we are talking is this one. It is called the Polimoni Packing. What is the Polimoni Packing? Now, how do we, I will essentially mention the problem, but here we are giving a reduction now from the previous problem, from the Jigsaw problem. Okay, so how can we, so the polyominoes are essentially like Tetris type of things. So this type of things that are coming. In Tetris, you have played, everyone, correct? Is there anyone who didn't play Tetris? Okay, that's, I mean, that's not bad. I mean, that I can tolerate it essentially. Still, I mean, waste time, but it's better than these Jigsaw ones. But anyhow, so consider, so these are the things that, these are the polyominoes that we have it. And you want to, again, put them such that we can form a rectangle. So we have a target rectangle, and then we want to have exact packing of this polyominoes, which I can define it, edge to edge joining of unit squares. So anything like this. But it, I mean, edge to edge, so it means that here you can have it. Just put a bunch of squares in any shape. Now, the problem is that, so as you can see that rectangle packing is a special case of this. Why? Because in rectangles you can put very small squares and then form any rectangle with a set of squares that you have. So, like the one that we were discussing, for example, AI was here and one here, so just put AI guys squares here. That's it. So, of course, this problem is harder than rectangle. But here, this is the issue. The pieces that we have in rectangle packing, the size of them, it can be large, it can be n. Where n is the size of the total size of the target. Because if you remember, the target here was n over 3. So the size of the target was n over 3, and each of these AIs were like large n. The question is that, I mean, this might be, I mean, these are not a very good puzzle that you have such kind of big things you want to put in. You want to make it a smarter puzzle or nicer puzzle. So the question is that these areas of these guys were order n. This is exactly the problem when we talk about the hardness. We really want to prove that even special cases are hard problems. Good. So what are the special cases? Yes, we know that if these are size n, then the problem is hard. But what about if the area is smaller? Can we prove like smaller areas for each of these puzzles and still they are fine? So that's actually interesting. So we can show that if they are the areas of each of these polyominoes are size polylog, then the problem is still. However, this problem is still open. That what about if the size are logarithmic, not log n to the 2? So a polylogarithmic means log n to some power greater. I mean, it can be greater than 1 as well. That we can do it. But what about if it is exactly logarithm? Or I assume probably even less than logarithm. Can we like square root of log? Can we show that in that case, even the problem is hard or not? Good. And it is not hard. I mean, I assume that probably would be hard. If not, that would be nice algorithms. That how do you want to do the algorithm? So now let's see. I mean, how can we get log n to the 2 here? So log n to the 2 is not hard. So you consider these guys as, so this is we had this puzzle, correct? And you remember that it has the tabs, the pockets, and these are like maybe some straight side. So that one we can, and each of these tabs, you remember it had what? It had color. So we mentioned there are 2 ways. Either you can have a cut or they have a special, either they have color or they have some special angle, for example, that they can match only together. Here, say that no difference, but say here, this is a color that this guy has. Now, this color was essentially from 1 to n. For some n, I think. For some, maybe it was n, which is this n is 4 times n prime or something like this. But this is linear in n, anyhow. So what can we do? We can actually form such a thing. We have log n by log n. This is some number, some color I. This color I, we will just put this one as a binary representation of that. So those places that are 1, you are coming essentially outside, and those places that are actually, yeah. So for this guys, I mean, for any places which is up, I mean, this I, it has a binary representation. I don't know. Maybe the binary representation was 1, 1, 0. So in this case, you have 1, 1, and 0. It means that you are not putting it. Similarly for this guy, and if it is a pocket, then you can do it the same thing. You will go down here. No. So you just do this binary encoding of these colors. And this is the way that, I mean, we are getting log n to the 2. Good. So the question that, I mean, can we do better than that? Again, I think log n, but even, I don't know, maybe square root of log n, maybe very, I don't log n. I think that's actually a nice problem to think about it. You should just double check because, I mean, I believe still the problem is open, the logarithmic area, but you should double check. But even logarithmic is solved. What about log n or square root of log n? These are the typical things actually we are talking about it. So this is the hierarchy that generally we talk about it. So we have one, order one. And we talk a lot. So this is the classes that you need to know. These are important classes or important numbers. We have one, order one. Then actually, let me go from the top. We have generally n, and like if the approximation algorithm for some problem has a factor n, is very bad. Then from n, we have n to the 1 minus epsilon. Then we have n to some constant. Then we have n to the epsilon. Then after that, we have, let me actually write it down, that might be better. So here we have n, then we have n to the 1 minus epsilon. Then we have n to some constant, which is c less than 1. I mean, much less than 1. Then we have n to the epsilon. Then we have 2 to the square root of log n. So these are for different problems. These are the typical bounds that obtain. So in that sense, of course, I mean, you can make your problem artificial such that any bound happen. But for natural problem, these are the bounds that we have. Then from this one, we have polylogarithmic. Then we have log. Then we have square root of log. Then we have log. Then we have log star. Log star means how many times I need to take log such that this number becomes less than 1. Then, I mean, from this one, sometimes we have this Ackermann function, which is even smaller than, so I will say Ackermann function, but it is very similar to actually log star. And then finally, we have order one. So these are the classes that like important bounds, I will call it. So these are the bounds that we are seeing a lot, essentially, in this class or in algorithm design, etc. So that's the thing that I mentioned. So if somebody says we have the polylog here for this problem, but then what about log? But after the log is square root of log, and then log. Can we get these things? How much encoding is needed actually to do that? Or that's interesting. So if the areas are log, can we say that we can solve the problem? Because if it is log, actually 2 to the log will become only log. So it's not a bad thing. Even exponential in log is not a bad thing. Clear? Ali, is it clear to you?
Yes, sir.
So he is here. Good. Okay, any question? These are actually interesting. These are sort of problems that you may think, and this is the way that we are thinking about it. So, and that is, I mean, you can think these are actually interesting because why this might be actually practical problem. Probably not as the add one, but it is. Because if these areas are smaller, you really, I mean, the company that makes this one can save essentially in terms of money or in terms of like smaller pieces they can do it. And still the problem becomes interesting. Because at some point, if the problem becomes trivial, then, and generally, if the problems are not NP-hard, it can be easier to solve. So we are interested in problems that generally, you want to solve the problem that it's not easy to solve. Not easy to solve is that generally should have exponential number of possibilities. Yeah.
Are these polynomial convex or they don't be
I think possibly they can be non-convex as well.
then can you just take some holes inside those.
Yes, possibly you can consider that. But again, think about this is the interesting. When you want to solve the problem, you want to solve the problem when there are holes. Yeah. So he said essentially, is it possible that is polynomial is something like this? So this part is empty. So let me just do it. So here the inside is empty. This is a hole in it. When you try to do algorithms, you want to solve even the problem that has such a case. But when you want to prove hardness, you want to say that even without holes, the problem are. Clear? Algorithm should be as general as possible, even if there are holes. Lower bounds should be as simple as possible. Even there is no holes, the size is small, everything. Can we still say the problems? Good. Any questions? Good. So let's go to the next problem. And these are the references. If you want, you can go and actually, they are also in the book. So there are more details about this in the book. In general, for this, we are mentioning a few games here, but Eric taught more in his class, but those lectures are also in the book. So you can read more from them and get fun, become familiar with that. So now let's closing the loop. So we had this loop that from this problem went to other problem, went to other problem. Now let's give this more one more reduction. Good. So what is this one? So now I want to give reduction from Polimoni Packing to Onsite Age Matching puzzle. Good. So what's the meaning of that? It means that I want to solve Polimoni Packing with Onsite Age Matching puzzle, the original problem that we had. So that's actually not hard again. So whenever you have this one, just give this, create this puzzle out of it. Note that in the Onsite Age Matching, we had only squares. But by definition, these polynomials are built of squares. So we just put the squares and then we are putting some unique colors inside such that they can only go together. And then we are putting some percentile things on the boundary such that they can match. Now, why this is interesting? So I love this bottom that you will say clear and clears everything. Is there any other? I think none of other like Hangout or Skype, none of them have these things that when you present, you can draw on the same page. Am I right? I have not seen any of others that they have. I think they might be patented by actually Zoom, because that's a very useful one that you have the slide. Also, you try to, like for example, at PowerPoint, if you use it, then in the PowerPoint, when you present it, then you can draw some lines there. But it's not the case that any page that you will share, you can draw in it, like the one that exists at Zoom, which is actually very convenient because they have the some kind of blackboard, if there's Jamboard or any whiteboard, anything they have it. But that is not that convenient because you need to go to that page and draw it there. But here, the same page that you are doing that, you can draw, and then you will clear it, clears everything essentially. I think that's a very nice feature that they have added and really helps in presentation because you can easily have a combination of anything that you want and write it down, something. Anyhow, so this is the problem that we have talked. We talked 4 puzzle type problems, which are all NP complete. And they are essentially, as I mean, this is also interesting. So these guys are a constant factor equivalent of each other. What's the meaning of constant factor equivalent? It means like if you have the number of colors is n, or the number of shapes or anything n, from one to other, you can have a below up a constant factor. Any important parameter of each of them, you just change it, goes like factor n up. And this was essentially the shape that we had it. So we had the three partition, then we mentioned on-site age matching as the main problem. Or actually, maybe before that, we had the rectangle packing as well. So this is the rectangle packing. So we had a rectangle packing. Then from there, we went to on-site age matching. So we showed that this problem is hard. Then using on-site age matching, we could show signed age matching is hard. Then using side matching, we could show that jigsaw problem is hard. Using jigsaw, we showed that Polimoni packing is hard. And then finally, we said that using Polimoni packing, we showed that even on-site age matching is hard. So we have this cycle essentially. And I mean, these are, lots of them are in this paper by Eric and his father. And you can see it, this jigsaw paper, also they are in the book. Any questions so far? Yes.
So is the reduction from Polimoni packing to unsigned edge matching it assumes that like the polynomials are very long.
Good. So you see, when you want to, so here we are saying that on-site age matching can solve Polimoni packing. So of course, if the size of them is log, then it can solve it as well. So in that sense, the log is not that important in that case. Correct?
But if it's smaller, then it could potentially be easier.
It could be easier if it is
if the sizes are constant.
Yes. But yeah, so I think you should, I mean, just do it and see whether this computation that you are doing, either it works or not. But again, these are nice problems. I mean, and you need to think about it. You cannot just answer because all of them, I mean, just you, this is exactly the issue also when you go with the, like people working, for example, in practice or industry. I mean, if you know some theory or algorithm, you will go there and you will talk with them. And then you think that, okay, after some work, you could solve the problem. You will come and say, okay, this is my problem. So, oh, by the way, there was one more condition that I forgot to mention to you. And that one more condition that you will add it may change the whole problem, becomes essentially from trivial problem to very hard problem. So it is important that like this condition might be one condition, but unfortunately it is not scalable like that in the algorithm design. One condition can essentially ruin a problem in the sense that we can, some problem that was completely solvable now becomes completely unsolvable, or it's a hard problem. So yeah, but you should, I mean, for each of them, you should see that whether you will put this additional condition, whether it changes the hardness or not. Okay, so the last one I mentioned at the beginning, that is also interesting. Now we have done some of these kind of gadgets that we have done it. I mentioned this add problem, that in the add problem, somebody may come and say, okay, you are solving the problem for this add packing, I will call it instead of rectangle packing. But these are like squares which are very narrow essentially. And then adds are generally not like that. These are more like squares. What about square packings? Can we show that problem is hard or not? Again, you can have the whole thing can be a square or it can be a rectangle. But we actually here we can even solve it for the case that the whole thing given a squares to a squares. Again, more special cases that we can show the problem is hard is better. So this is the problem. So this is the paper. This is the paper that say that packing a square into a square is actually a strongly NP-hard. And again, a strongly NP-hard comes because we can do it via tree partition. And I mean, there are, as I mentioned here, this is the previous one, scheduling square jobs on a grid supercomputer, but more importantly, I would say packing ads. Good. So the first thing is that we need to create so we want to get this problem a reduction from, so we want to get a reduction from which problem? Yeah, but yeah, so that is the, I mean, it is important that like when you work in this NP-complete problem, generally this is a large set of NP-complete problem like this. You want to find it is closest to your problem. Then your work will be much easier. You can, of course, I mean, anything almost comes from tree-sat, even tree partition, because tree-sat is the, or SAT actually, that came from equivalence of the Turing machines. But then you need to do all these gadgets guys that they have done. It would be very super complicated paper and probably still gets rejected. That's also another interesting thing because, oh, you didn't do the correct thing. If you use this problem, that would be much easier. Unless if you do it for, there are 5 problems like graph isomorphism, factoring, and a few other problems. This is from the original book of Gary and Johnson. But still, we don't know whether this problem are NP-hard or not. Therefore, that you will solve, you will get best paper award. For others, you will get rejection. Especially if you, I mean, it's part of other paper with other results, that should be fine. But if you prove a complicated thing using tree-sat, the people, in some sense, laugh at you. And unfortunately, they reject the paper. So you didn't do the correct way. Because I think, in some sense, I mean, they are right, because you ignored the science in some sense. Good. So yeah. So this is the reduction from rectangle, essentially rectangle packing. Rectangle packing, and that's exactly the reason actually that we. So, that's the reason that we are working with this. Problems. So we introduce these new problems such that we can use them. So for like in some sense nowadays, if you work like more this type of packing geometric thing, you should actually go to rectangle packing. That's the problem. And there also you can assume that this problem that all of this guy had width 1, still it was hard. That might be easier. You don't need to have width 2 essentially. Problem. Yeah.
Is rectangle packing considered the best geometric problem?
I mean, I don't know best, but it's one of the, I mean, it's very nice essentially. I mean, that's a good problem to think about it. Surely there are lots. I mean, the NP-complete problem, the number are huge. That's actually interesting. Almost any practical problem that you are considering is NP-hard nowadays. Like the most complicated algorithm, which are polynomial, are two things. One is the maximum matching, and the other one, it is the matroid intersection. That is also somehow related to matching algorithm for bipartite graph. But these are the most complicated algorithm. Interestingly, I will mention that I think this is the first algorithm for matching. This is for weighted matching in general graphs. That has been done by Jack Edmonds. This is actually a very nice article. Just search this article, Jacquet-Mon's maximum matching, weighted matching. To just, I mean, I want to just say maybe briefly the things, but just go and read that things. That's very nice. He has done it in 1960, these results. In 1960, that he has done these results, there was no concept of polynomial time algorithms. In the paper, he wanted to mention that why this is a good algorithm to the mathematician. So mathematicians say, okay, you want to find the maximum matching. What is the maximum matching? Is that you want to find a set of edges that they don't share an edge. And say the graph is weighted, you want to find the maximum size or maximum weight matching. So to them, to mathematician, he wanted, okay, we will find it in naive. So why do you care about it? Just try all possibilities, take the best one. It's a somehow solved problem for them. He tried to say, no, why my algorithm is better than that. Actually, I think that's one of the very early versions of this concept of polynomial time algorithm and computing. And I think he contributed actually a lot because this algorithm, he got it in 1960, is still, I don't know, after 62 years, that is one of the most too complicated algorithms that we could solve it in polynomial. And I remember when I was doing this, I mean, be prepared, for example, for this informatics Olympiad that I have done in 1997. I talked with some of these people, and some of them said, "Oh, actually, we have been. I think probably all of you were born after 1997." And then I felt, oh, actually, maybe I'm very old, but I'm not that old. At least I don't feel that. But anyhow, so for that one, I remember anytime that I want to get to the mode of coding, I have done two problems there: bipartite matching, bipartite weighted matching, and the other problem was unweighted general matching. I have never done general weighted matching. That's much more complicated. I have done it when I was a master student at the University of Waterloo. I had a combinatorial optimization. There, I remember that I have written the algorithm. I think it took maybe around something like around 17 pages. I was writing it by hand as well to describe that algorithm and say why it works. And he has done it in 1960. There was not much computing going on. And I think really he deserves to get a Turing Award that I will mention. There are some issues about his personality, but other than that, I think his contribution was great because he solved something that 60 years from now still is the most complicated thing that the people can solve it. I think that really deserves. And he explained the concept of polynomial time algorithm at that time, that why matching this algorithm that I have done, it is actually the good algorithm and different from the way that mathematicians are thinking about it. Anyhow, so let's come back to these things. I just wanted to mention, the problem that can be solved versus not solved. This gives you some idea that which problems are the hardest problem that you can do it in P. Almost all other problems are NP-hard. So there are so many, to answering your question that you asked, what is the best geometric problem? There are so many NP-hard problems. Almost anything is NP-hard. And then, of course, this is the one problem, but I'm sure that there are lots of other problems that you can think about it. And we talk actually about some other problems as well, but yeah, so this so far is that's the best problem.
And I was wondering, for environment problems, everything eventually from partition or from SAT. So yeah. For geometric, what does it eventually lead down to?
Yeah, I think surely the rectangular packing is an important problem, but there might be some that I don't remember it now. Essentially, you can just search what are the problems, and you can. That would be, a good search actually. Google knows everything almost nowadays. Good. So yeah, now let me just mention this one. How can we do that such that we can finish this one? So first we need to create a rectangular space. So correct. So what was the rectangular packing? We want to solve the rectangular packing using packing squares into squares. So here first we need to create our target rectangle, which, if you remember, was something like this. Was n over 3 here, and t. T was the size of each bin in the 3 partition. We will put in 3 items in each bin. Good. So this is the square that we are doing. This is the very special square. I mean, this is done in this paper, actually. It's a nice one. So you put this type of squares, like these are the size of the squares. If you put it together, you can see actually this is the, depending on x, you have actually a square of, from these squares, you can create this area, which is the rectangle that you want. Good. And these are somehow unique. These are so big that that's the only way that you can put it. So that's the frame of the rectangle. So the rectangular packing that now you want to do it is this area. Good. Is it clear? So you will put such a big things that all of them are squares. At the end, you are forced to put them in such a shape such that this part becomes empty. This is the part that we will use it for a square packing, for the rectangular. Now let's see, what do we do after that? Good. Now, for we are putting squares of the, actually, I mean, here, yes, so this one, sometimes actually you can do it in some sense, a square packing, and we may use the proof of rectangle packing instead of just the problem itself. So the way that we have done it from 3 partition, we can just use the proof, or we can use a special case. So it is so special, which is very close to like 3 partition. In some sense, I'm using the proof of rectangular packing and the 3 partition in some sense interchangeably in this presentation that I mentioned. Okay, now we had essentially, so in the 3 partition or in this problem on this square packing, on rectangular packing, we have this concept of AIs, correct? AI was that, which was the size of each number that you want to. Now, you are putting squares of dimension AI plus B, where B is a huge number. We will decide how much should be B. Good later. So now we will pack them into rectangles of height 3B. Good. What is this 3B? This actually, this is this area. So this area is essentially, if you zoom in, it becomes like that. Because this is a rectangle. Now in this rectangle, we want to put squares in it. Again, everything is squares. But because we put it this one, we put it such a way that this part becomes empty. Now we have some other squares that we want to pack it, and then from that we want to solve the problem. So how do we do that? So we say that essentially the height of this is 3B plus T. So each of these guys, each of these squares that you have it, the size is AI plus B, where B is a big number. Again, the same thing that we have done for 3 partition. You remember we added one big number such that all of this becomes noise. Good. Now, how do we do that? So this, we will say that this guy, we want to have 3 partition. This would be 3B plus T, correct? The height of this guy. Then you put the height of this guy 3B plus T. Then what will happen? No, we have all of them are squares. Note that, I mean, the sum of the height of these guys would be 3B plus T. 3B because each of them has this big number. What is T? T because the sum of these AIs should become to T. Now, in some sense, you are forced to put these guys together such that, and say that these guys, I think the size of this guy is also, I will say, probably B plus T or something like this, or B plus max A. Good. Now, so in some sense, so this was the whole things, it is like that. And then for each of them, we are putting this 3b plus t things. And now, if we can put 3 guys that the sum of them are become to t, then the height of these guys becomes equal to 3b plus t. However, these are not rectangles, these are squares. So there are some slopes here. The question that maybe can we use this one to put some other squares there? Because that should not happen. If this happens, this is not a reduction. You can, in some sense, we want to force that in each of these essentially slope, we are putting exactly 3 squares, and the height of them should be 3b plus t. That's exactly the way that shows the problem is hard. Now, let's see what is the total, so it's total slope that we can have it here is okay. So we have this kind of columns, and we want to consider how much slope, how much essentially things that we will have empty space. A slope means essentially empty space. So the empty space here would be max A. Why? Because because the difference between the length of this square, the size of this square, is it can be at most max of A. Max of A is this number. So A is the set of these numbers. So at most this bigger square and this smaller square, the difference between them can be A. So that would be max of A times 3b plus t. So this area that we have it here, it can be at most max of A, because this is the width of it in some sense, and the height of it is 3b plus t. So that's the total area that we have. If we are making sure that this area is less than b squared, it means that we cannot actually put any square here. Why? Because this b that I mentioned before, that b, we are taking b huge, such that this is smaller and we cannot put any other guys there. So as long as the max A times 3b plus t is less than b squared, we are fine. To do so, we need to only take b greater than 4 times 9. Good. So so when you put it such a large number, then we cannot essentially put in this empty space to put another one. And it is so in the slope here, we cannot do that much. You can also think about that, why we cannot shift this guy a little bit. That needs also some proof. But there are, so this is the general idea. This was the whole proof, was the whole paper was about these things, which is interesting. So you can see more details in the paper, and I think there are some more details also in the book. But probably the complete one would be in the paper that you can read it. But these are somehow general ideas that you will put it such that you will make sure that from this squares, we are creating this rectangle, target rectangle, and then we are putting squares also in it such that we can solve the problem. And we are somehow, in some sense here, we didn't use this rectangle packing directly, but we use the proof that we have done. So the same proof actually carries on here with some more details. Good. Ali, are you still there?
Yes.
Okay, good. Great. So any question? Yeah, good. So I think that just clear everything. So we are done here. Next session, we are talking about 3SAT, the other important problem. This one. And of course, we are starting from this, we are building other problems, but there are lots of others. I try to give the one that is generally used the most. But there are lots of other problems that, again, when you want to prove the NP-hardness, generally, may help to at least see the problem which is similar to your problem, because then you might be able to get much easier reductions. Even, you may not get the exact problem which is useful. It might be good to read the way that they are using for the gadget. Like, for example, here, I use the fact that I use the proof of rectangle packing to get the results, not maybe exactly the rectangle packing. So if I know the proof, okay, this is the proof, I can maybe massage it and then it works for my problem. Okay, so I think given this, I think we can finish the session, and then see you next time.